In the last two videos, we defined several risk measures, namely value at risk, tail value at risk, conditional tail expectation, and also expected shortfall. In this video, I'm going to discuss some basic relationships between these few risk measures. So there are altogether three important relationships between them. So first is about T-VAR. So the first equation says that the tail value at risk of x at level alpha can be decomposed into the value at risk plus 1/1 minus alpha times the expected shortfall. The second formula is very similar to the first one, except that it is for conditional tail expectation. And here in the denominator, instead of putting down alpha, we put down fx of the alpha value at risk. In particular, I hope you still remember in the last video, we showed that if the distribution of x is continuous at level alpha, then fx at VAR alpha is just alpha. Therefore, the right-hand sides of these two equations are exactly the same. Therefore, when x is continuous, T-VAR and CTE are the same. The last equation relates CTE and T-VAR. So in general, CTE at level alpha is the same as T-VAR at another probability level, and the level is given by fx VAR at alpha. So now let's take a look at some examples. So here we consider an exponential distribution. So we want to find VAR, TVAR, CTE, and also ESF, expected shortfall, at level P. So first of all, we can observe that this CDF is continuous and it is strictly increasing. Therefore, finding VAR is very straightforward. All you need to do is to solve an equation like this. You set the CDF to the probability level P, and then you solve for Y. So we set this to P, solve for Y, we get this expression. And this is exactly the value at risk of the variable Y at level P. So now we know how to find VAR. Next, we consider T-VAR. Okay, so by definition, T-VAR at level P is the integral of value at risk from P to 1. So here, beta is the variable of integration. We integrate the level beta from P to 1, and then divide this integral by 1/P. So in the previous page, okay, we know the formula for the value at risk at any level P. So we substitute this expression and this integral, and then we obtain this. So we need to integrate this -log1 minus beta of alpha with respect to beta. You can do this by integration by parts. Here I give you an alternative way to find the tail value at risk. So in this case, we make use of the first equation. So T-VAR is VAR plus expected shortfall over 1 minus the probability level. We have already derived the formula for value at risk. So in order to find tail value at risk, we need to know the expected shortfall. So that's why here I find the expected shortfall of variable Y. So by definition, expected shortfall is E of Y minus the value at risk and then positive part. Okay, and then we try to evaluate this expectation by conditioning. So we condition on whether Y is greater than the value at risk or Y less than the value at risk. Of course, in the second case, when Y is less than the value at risk, the positive part will be 0. That's why the second term disappears. We only have the first term. So it is E of the shortfall given Y greater than the value at risk times the corresponding probability. And here we make use of one important property about the random variable Y. Because Y is exponentially distributed, therefore Y has the so-called membranous property. So condition on Y greater than this level, Y minus this level has the same distribution as the original random variable Y, that is exponential with mean 1/alpha. Therefore, the expected value of this random variable is just 1 minus alpha. And then for this probability, it is simply given by the survival function of the exponential random variable y evaluated at this point. Okay, so that's why it is 1 minus fy evaluated at the value at risk. And you can calculate this easily. It will be 1 minus p over alpha. So now we make use of our formula. T var equals var plus expected shortfall divided by 1 minus probability level p. var, we know what it is. And then expected shortfall is here. And then over 1 minus p is 1 over alpha. That's why it is given by this expression. Next, conditional expectation. Because y is continuous, so for continuous variable, we know that T var equals CTE. Therefore, in this case, for our exponential random variable y, which is continuous, so we know that CTE is the same as T var. Now let's take a look at another example. So here x is uniformly distributed between 0 and 100. And we consider random variable y, which is given by x minimum 90. Okay, so you can treat 90 as the policy limit. So y is the limited loss variable. So we want to find the tail value at risk of this variable y at probability level 0.8. So to solve this question, okay, we first plot the CDF of x, which is a straight line between 0 and 100. And then because of this transformation, the CDF of y will have a jump. Okay, it jumps at 90. Okay, it jumps at 90 to 1. So this is the CDF of the random variable y. So now to find the T var at level 0.8, again we make use of the formula. T var is var plus expected shortfall over 1 minus probability level. So first of all, what is the value at risk at level 0.8? So hope you still remember, to find this value at risk, we draw the horizontal line at probability level 0.8. Okay, and then now we see there's one intersection. And then we go down, this point is 80. So this 80% value at risk is 80. How about expected shortfall? By definition, expected shortfall is E of the shortfall, which is given by y minus the 80% VAR positive part. And this 80% value at risk is 80, so it is E of y minus 80 plus. And in the very first chapter of this course, we know that this kind of expected value can be obtained by finding the area from 80 to infinity above the CDF curve. Okay, so now we need to find out the area of this part. So from 80 to infinity above the CDF. Okay, so it will be given by this region. Okay, so the area of this region is very easy to compute. So we put it here, and then we can get 87.5. So the last example is more complicated. It is about normal random variable. We want to find the CTE. Okay, so in this case, first we find value at risk. So to find value at risk, we set the CDF to alpha, and then we try to solve this equation for t. So to solve this equation, we first write it as the probability that x less than t, and then we standardize both sides. The left-hand side becomes a standard normal random variable. Therefore, the probability here is just the standard normal CDF evaluated at this point, t minus mu over sigma. So this phi, capital Phi, is the standard normal CDF. It equals alpha. And remember, we want to solve for t, so we consider the inverse of both sides. So we consider phi inverse of both sides. Then t minus mu over sigma becomes the CDF inverse of alpha. And then we rearrange this equation, we obtain t, which is just the value at risk of x at level alpha. So now we have the value at risk. So by definition, to find T var or to find CTE, remember we want to find CTE. And because this is continuous, so CTE equals T var. And by the definition of T var, okay, so for example, we can look at here. So by definition of T var, you can integrate the var. Okay, so we can use this formula, but we have a problem here. So in the case of normal random variable, var is like this. So if you want to find tail value at risk by definition, you need to integrate this over alpha, which is very difficult, okay, because we don't have a closed form expression for this phi inverse. Therefore, in this normal case, we go back to the definition of CTE. So CTE by definition is E of x, given that x is beyond the alpha value at risk. And then now for x, I write it as mu plus sigma times this standardized variable. And then for the event here, the same. I standardize both sides of this inequality. And then after standardization, it becomes phi inverse alpha. And we notice that x minus mu over sigma is just a standard normal random variable. So I replace it by capital Z. This capital Z is a standard normal random variable. So I replace them by Z. I put mu and sigma outside the expectation. So CTE is given by this. Okay, so now we can find out the conditional expectation here by first principle. Okay, so all we need to do is to integrate Z times the standard normal density from phi inverse alpha to infinity, divided by the probability of this event. The probability of this event is just 1 minus alpha. Okay, and then when we try to integrate this, you can easily find the antiderivative of the integrand, which is like this. And then we need to evaluate it at Z equals phi inverse alpha and infinity. So it is very straightforward. So when Z equals infinity, E negative infinity is just 0. So we only have this term, putting this phi inverse alpha in this standard normal PDF. Okay, so it becomes 1 over 1 minus alpha times this small phi. This small phi is the standard normal density evaluated at this point. Okay, so putting this back to here, we obtain conditional tail expectation, which is mu plus sigma over 1 minus alpha times this thing.